Fundamentals of ECG, determination of main electrical axis. Main electrical axis. The main electrical axis is going to give you about the same position, or the anatomical axis is roughly about the same. However, we are not interested in seeing what is the anatomical axis of the heart, but we want to see whether we do have some pathological electrical impulse generator problem or not. If we do have a normal axis, the normal axis is ranging from 0 to 90 degrees. Well, that can be explained anatomically, so there is no pathological condition can be. However, if the axis, the main electrical axis, is extremely leviated to the left or extremely leviated to the right, for sure there is no anatomic situation that is going to explain this one. However, if we do have this area, for example, as a left deviation ranging from 0 to minus 30, this can be explained by anatomical situation. For example, an elderly, fat, for example, patient with a big belly, yeah, it can be horizontally shift the axis so the diaphragm can push up the heart. So this way the electrical axis can be in the range of 0 to minus 30. However, if the patient is a skinny one, a tall one, and young one, for sure this can be pathological condition as well. Similarly to the right deviation, if somebody is a fat and obese one, for sure it cannot be, because there is no way that the patient can have this kind of very high axis ranging from 90 to 110. Now, how we are going to calculate this axis? Basically, we are going to use this dipole model and this vector model. What you learn in physiology, what they did, they used the Einthoven triangle. They used only 1, 2, and 3, and they constructed the axis. Much easier way to do it if we are going to summarize, or are going to draw a different panel for these all 6 leads and shifting everything to the same endpoint. The all vector is shifted to the endpoint parallel, and this way we're constructing this called hexaaxial reference system. In this system, AVR represents minus 30, lead number 1 0, lead number 2 60 degrees, AVF 90 degrees, lead number 2 120 degrees, and AVR 210 degrees. Now, as you use, for example, for the Einthoven triangle, what we did, we put the sum of the QRS complex to lead number 1, lead number 2, lead number 3, and we summarize the vector, and this is how we got this main electrical axis that is substituting the all cycle within the QRS complex. Now we do have a two easy way to calculate the axis. One is called the Equiphasic approach, and other one the Quadrant approach. Let's look at first the Equiphasic approach. Equiphasic approach means that the QRS complex, the sum of the QRS complex, be about 0. So if you are summarizing the positivity and negativity in this wave, that roughly the sum should be 0. As you're looking at the first one, mainly this is positive. The next one, mainly negative. And here, the third one, this could be equiphasic one. So the net should be 0. What does it mean, and how can we use this one? When we determine which lead contains the most equiphasic QRS complex, the fact that the QRS complex in this lead is equally positive and negative indicates that the net electric vector, or the overall QRS axis, is exactly perpendicular to the axis of this particular lead. Now examine the QRS complex in whichever lead lies to 90 degrees away from the lead identified in step 1. If the QRS complex in this second lead is predominantly positive, then the axis of this lead is approximately the same as the net QRS axis. If the QRS complex is predominantly negative, then the net axis lies exactly the opposite 180 degree from the axis of this lead. Now let's looking at here we do have a tracing. First of all, to determine the main electrical axis, we only using the frontal panel. We are not going to use the horizontal leads. So look at lead number 1, 2, 3, AVR, AVL, AVF, and look at the QRS complexes. Which one is closest to the zero? So which of the sum of the R and S is close to the zero? AVF. What does it mean? It meaning that we do find an equiphasic in AVF. Okay, so if the AVF is equiphasic, meaning that the axis, the main electric axis, has to be perpendicular to this lead. This is or 0 or 180. So we have to look at lead number 1, for example, whether it's positive or negative. Lead number 1, as you see here, is positive. So if lead number 1 was positive, meaning that this electric axis should be parallel with lead number 1, so the axis has to be 0. In another tracing, let's choose the most equiphasic lead. 1, 2, 3, up to the AVF. Lead number 2 is the most equiphasic one. If lead number 2 is equiphasic one, we have to construct a perpendicular to lead number 2, that is AVL, and opposite 150. Whether this is the axis as minus 30 or 150, we have to look at AVL, whether positive or negative. If it's positive, this means minus 30. If it's negative, 150. AVL was positive, so meaning that our axis is at minus 30 degrees. Another method is the quadrant approach. The quadrant approach is based on we are going to divide the circle into 4 equal quadrants. We are going to use 2 leads, standard 1 and AVF. And a combination of these 2 leads, we have 4 quadrants. For example, if we do have lead number 1 positivity and AVF positivity, that's the range is normal. If we do have lead number 1 positive, AVF negative, we do have left axis deviation. If we do have lead number 1 negative, we are on the right side, and AVF is positive, that means right deviation. Usually in this upper part between 180 and minus 90 or 270, there is no axis, so basically it cannot determine or doesn't have any meaningful. Let's look at the normal axis. So we said that lead number 1 is positive, so we are on the left side, and AVF is positive, and because these two should be true, only the common part is true, so the range is from 0 to 90. So by looking at these two, immediately we can state the axis is normal. Next one, extreme left deviation. Extreme left deviation is ranging from minus 30 to minus 90. Okay, we have to be on the left side, so lead number 1 has to be positive. Because we are up here in this area, AVF should be negative, so the common part is between 0 and minus 90. Whether we are over minus 30 or not, which lead is perpendicular to minus 30? Lead number 2. So lead number 2 should be negative, and this way we do have a portion that range from minus 30 to minus 90. In the case, lead number 1 positive, AVF negative, lead number 2 is positive. Left deviation between 0 and minus 30. Lead number 1 should be positive, AVF should be negative, and because we want to have this, lead number 2 should be positive. Right deviation, we are on the right side, so lead number has to be negative. AVF has to be positive, the common one from 90 to 180. Extreme right deviation, well, normally the extreme right deviation starts from 110 and goes all the way 180, but it's very difficult to determine 110. However, we do have a lead that is exactly perpendicular to 120, and that's AVR. So look at AVR. If AVR is positive and lead number 1 is negative, for sure we do have an extreme right deviation. Right deviation, that's ranging from 110 and 90. But again, it's very difficult to count up to 110. But if AVR is negative, we are between 90 and 120. So that's we can call as a right deviation. Of course, this is almost impossible to calculate exactly the 110, but in this case, we can say that it's only we have a right deviation. Let's look at some examples. Okay, let's look at lead number 1. It's negative, so we are on the right side. AVF is positive, so this is a right deviation. Look at AVR. AVR is equiphasic, so meaning that we do have 120, so we do have an extreme right deviation. Next one, lead number 1 positive, AVF negative, so we have a left deviation. Look at lead number 2, it's positive, so that has to be only a left deviation, it can be normal. Next one, lead number 1 positive, AVF negative, lead number 2 negative, so this is an extreme left deviation or pathological left deviation.